the So the question is to find the electric potential of a point charge sitting in a distance d above a linear dielectric media with a dielectric susceptibility chi0. So we found the potential to be given by this, and from here we determine QA to be that, and QB to be that. So that's the first part. The second part is to find the force that this point charge Q would experience because of the bound surface charge that you would have here, the negative bound surface charge created by the electric field of the point charge Q. This point charge Q would experience an attractive force. So it would be attracted to this surface. So we want to find that force. So when we determine the potential here, we say, for the potential at the point outside here, we can think of the bound surface charges on this dielectric surface to be represented with an image charge which we call QB, located at a distance d away from the surface, right? So if we can find that charge, the total bound surface charge here, which can be assumed to be located a distance d away from that, if we know that total charge, then it's easy to find the force that this point charge would experience. So it's just simply a force between 2 point charges separated by a distance twice of d. So in order to find the force, what we have to do is to find these total bound surface charges. So to find the total bound surface charges, first I need to find the surface charge density. So how do I find the surface charge density? You can do it in two different ways. I did it in two different ways in the lecture note, but I'm going to do it here just only the first way. So the first method is, how do we find this bound surface charge density first? This is for part B. The bound surface charge density, sigma bound, is defined as what? It's defined as sigma B equals to the polarization vector dotted with n. Now, the polarization is related to the electric field, right? For a linear media, how do we express the polarization? The polarization P is equals to epsilon naught times chi E, the electrical susceptibility, times the electric field. All right? So this is evaluated when? At the surface, right? At Z equals to 0. So if I know the electric field somehow, then it's easy to find the surface bound charge density. So you can find the electric field using the electric potential in the polarizable media and evaluate that electric field on the surface. That's one way to do it. So if you determine the electric field in this region, in the polarizable media, because the polarization is inside the polarizable media. if you determine the electric field inside here, using the electric potential, this one, all right? So inside the polarizable media, this is what we use to find the electric potential. So if you use this, take the gradient, evaluate it at t equals to 0, then you can find the electric field, and using that polarization, you can find the bound surface, the surface bound charge density. So I've done that in the lecture notes, you can look at it. But the way I want to do here is just finding the electric field in a different way without using the electrical potential, the way that Griffith did in the textbook. So when we say the electric field on the surface, so how many electric fields basically, just forget about the dielectric media and think of the effect of the dielectric media is to create the surface bound charge density, right? So you put this point charge, what happens? The electric dipole moments, they line up, and inside the volume, since it's a linear dielectric media, inside the volume, the charges disappear, and you would have only surface charge at the top, right? So that's the effect of this point charge on this dielectric media. So when we talk about the electric field, then it's going to be the electric field of what and what. If we talk about the electric field on this surface, one is the electric field of the point charge, right?
And the electric field would be balanced surface.
Exactly. So if I find the electric field of the two, then that means I know the polarization, and then I can express the bound surface charge density. Now, let's assume that the bound surface charge density here is sigma b on this one. Assuming that it's sigma b, basically the situation can be reduced into this. So, infinite surface charge with, that's not uniformly distributed, but it's a negative charge, sigma b, and your point charge along the z-axis, okay? X, Y, Z, and your point charge Q. So basically, the problem reduces to that. So you can think of this region in empty space, and this empty space. So the point charge, it just creates these bound surface charges, and that's all it does here. So then how do you describe the electric field on the surface? So the electric field on the surface is going to be then on the surface is going to be E equals to the vector sum of EQ, right? The electric field due to the point charge, and the electric field due to the bound surface charge, sigma b. All right? Now, remember, since we are interested in sigma bound, and sigma bound is the polarization dotted with the unit normal vector, and the polarization is the function of the electric field. So when you take the dot product with the normal vector, the unit normal vector, what survives is which component of the electric field?
Z.
The Z component, so the normal component. So I can just focus only the normal component of the electric field. So E perpendicular is gonna be EQ perpendicular and E sigma B. Well, for this infinite surface charge, it has only a normal component, right? So for if you have infinite surface charge, the electric field is always perpendicular to the surface. We have seen that one. So you don't have to the perpendicular. Now for the electric field of the charge here, if I just assume that this is where I want to evaluate the electric field at some distance r from here, so this distance is r, and if I call this angle is theta, all right? So what's gonna be the electric field, the normal component of the electric field of this point charge at this point? Well, first, if I want to the electric field at this point, what's gonna be? So this length is gonna be root of r squared plus g squared, right? So the electric field at this point, E in general, is gonna be Q over 4 pi epsilon naught 1 over root of r squared plus g squared. Right? So that's going to be the electric field of this point charge at this, right? You agree? Now, what's going to be the z component? The z component is going to be this magnitude times cosine of theta, right? And cosine of theta, how do you express it in terms of this and that? Or this length and that? Yes. Cosine of theta is going to be d over root of r squared plus g squared. So d then for EQ normal, the normal component of the electric field, then I can write that Q, the magnitude of E cosine of theta, which is going to be Q over 4 pi epsilon naught 1 over r squared plus g squared times cosine of theta, that's going to be d over root of r squared plus g squared. So which means EQ normal becomes QD over 4 pi epsilon naught times r squared plus g squared raised to 3 over 4. Right? So we are talking about here just the magnitude of the normal component, okay? And for, if I assume that the surface charge density here is sigma b, then how can I express the electric field magnitude due to this infinite surface charge density sigma b from what we discussed in the previous chapters?
Sigma b over
Yes. Yes. So E sigma b is gonna be sigma b over 2 epsilon. Yes, remember there is a factor, so if you apply Gauss law, you can be sure. Now, we know the electric field due to the bound surface charge density and the electric field due to the point charge. So the net electric field at this point on the surface is going to be the sum of the two. So I can write E normal. Okay, first let's talk about the direction.